In this video, I'd like to go through the shallow plane truss problem that we have already solved before using the arc length method. I would like to use this as a case study for remarks for nonlinear buckling analysis. Let's look at the problem once again. We had the case of a truss, which was of a hinge condition. You had two trusses which were connected to each other at a certain point, where a load was applied. Let's call this load F. And depending on the load that was applied on this problem, we could follow a certain displacement behavior, which, for example, could look somewhat like this before it went into sudden change. Now, in this path, of course, we can call this the primary path. There was a point where it reaches the limit, and that was called the limit point. Now, there could be that there might have been a bifurcation point at a certain point where it could have become unstable, which would have given rise to a secondary path, as we have seen before. Now, the reason why I'm using all these secondary paths and buckling is that this problem no longer should consider the elements to be trusses, but to be beams, so that they are capable of buckling. So that means before the limit point, they can also buckle. Now, there is a second condition, of course, for the same beam arrangement. We can also say that instead of it being just loose where the force is applied, you could have a certain spring of a certain stiffness K, which is attached at the point of the hinge. Now, if there is a certain stiffness that is attached to it, then the behavior of the load displacement curve is going to change. You can, of course, have the same primary path limit point, but at the point of bifurcation, because you have a stiffness that is attached to this hinge point, you do not lose the stiffness, but you gain some stiffness by going upwards in the secondary path. So the secondary path becomes different in both the cases. So what you are getting in terms of a secondary path is a characteristic of a structure with or without the post-buckling strength. So in the first case, you do not have any post-buckling strength, so it keeps on reducing. But if you add the central spring of a suitable stiffness, the secondary path rises, indicating that there is still some post-buckling strength in the structure. Of course, the primary path will cease to exist, so you will never reach that limit point L, which you had seen before in the case of trusses, for example. Now, what's very important to know is that the behavior is strongly influenced by all kinds of changes that are made in the structure, even small changes like you've already studied. If you're going to change the shallowness of these trusses, there's going to be a change. If you have a column buckling strength which is different, that means each of the members have a different kind of a strength, then of course it's going to be different again. And the stiffness of the central spring K also makes an influence on the post-buckling strength of the structure. So in the same way, if you consider thin shells as well, the behavior is going to change with small changes happening to something around the structure. So it has a lot of sensitivities attached to it. The moment we are going to use linear bifurcation, we should always be aware that it will overestimate the limit point load. And the reason is imperfection sensitivity. And that's the next topic for the remarks I would like to make on nonlinear buckling problems. So when you say that I'm going to use linear bifurcation, as I showed you before on how to calculate linear buckling loads for linear bifurcation problems, then in linear bifurcation problems, the limit loads that are calculated are overestimated. The reason is that we are considering perfect conditions. So eccentricities, perfect geometries, etc. However, in reality, a structure always displays some kind of imperfections. This is a term that you will come across every time when you are studying anything to do with buckling. The imperfection sensitivity states that the collapse load is strongly going to be affected by any kinds of changes that happen in geometry, in orientation of loads, also by distribution of loads, or even the support conditions, where exactly you're supporting the structure. The limit point of an actual thin-walled shell, for example, when you calculate it using a using a linear buckling analysis, let's say that your load that you get is a 100% of the limit load. That's what you calculate using your finite element analysis. However, with all the imperfections included in your structure, your limit load with imperfections for a real structure may hardly be 10% of your limit load that you've calculated. Even by heroic effort in the lab of creating the best possible geometrically perfect structure, you may even rise to a 50%, but that is actually looking very good. So you can imagine that small imperfections are going to cause a large change in the buckling behavior and the results that you're looking for. To summarize everything in a graphical format, we can imagine that you have linear analysis, where you get a linear bifurcation point, which is where the analysis stops. On the other hand, you have your nonlinear analysis, which may give you sort of a behavior like this, where you get a limit point over here. Further, this only defines a perfect structure, but a real structure may behave like this. So there are big changes by making small irregularities in your structure. Now, in finite element analysis, you may say, okay, that might be difficult now to achieve because I will always consider a perfect structure, so I'll never get close to my analysis. So should I just assume 10% of the limit load and say that is the actual buckling limit load value that I should use? Well, you are able to introduce small imperfections into a finite element model very easily. They can be introduced deliberately, right? You can either make some geometrical irregularities, you can also add additional loads, and you can also add additional support situations for making geometric imperfections of interest. The other way to do it is to carry out a linear analysis first and use the results or the eigenvalues and the eigenmodes and use those as imperfections in your input files. We will do some examples with the plate problem, the composite plate, and hopefully we will learn a bit more about how the imperfections actually affect the problem.